This slide shows the conventional one Neumann stored program control SPC computing model with a single CPU. The service workflow is executed as a serial instruction set and provides a fixed behavior. In this model, service and its management are intermixed in a serial fashion to create the required service behavior. For example, when input is read from a file, the file open is part of a service instruction set. With the introduction of multi-core processors, parallel programming techniques allow creating multiple behaviors. However, service and its management are still serialized and are part of the service instruction set. The complexity increases with a distributed transaction that spans over a network of SPC nodes. A distributed transaction is a highly temporal phenomena. To assure the integrity, system-wide connectivity and coordination are required with a sense of time, history, and synchronization between various tasks performed by a group of loosely coupled elements. The DIME network architecture addresses the management of a distributed transaction by using a signaling network overlay of one Neumann stored program control SPC computing nodes to implement dynamic fault configuration, accounting, performance, and security management of both the nodes and the network based on business priorities, workload variations, and latency constraints. There are two ways to implement a DIME. In a conventional OS, a process is encapsulated as a DIME that can be programmed to self-configure, self-monitor, self-protect, self-optimize its performance based on business priorities, latency constraints, and workload fluctuations. In addition, a network of DIMEs can be programmed to execute a managed workflow also based on business priorities, latency constraints, and workload fluctuations of the distributed transactions. The second way to implement it is in a native operating system specifically designed for many core servers. We have implemented one such operating system called Parallax in assembler language with C and C++ interface. The architectural resilience of cellular organisms is attributed to the dynamic coupling between various elements of these systems, where each change in one element continuously influences every other element's direction of change. It has to be accounted for in any computational model that includes systems' sensory and monetary functions along with computational analysis. The DIME network architecture brings this architectural resilience of cellular organisms to service management through a network of managed Turing machines that exploit the parallelism of many core processors and the signaling abstractions.